Hello, so this video will be hopefully a one video that covers most of how to solve equations that have algebra in them. And I'm going to start from relatively from scratch. There will be a bit where we talk about gathering like terms, and I want to push you over to a video I've already made, which is all about gathering like terms, which goes into much more detail than I can do here. Otherwise, I just repeat myself too often. Okay, so before we get to equations with algebra in them, let's just lay down some fundamentals here so you're not confused from the very beginning. I want you to keep in mind that whenever we use letters in mathematics, these are just temporary placeholders for a number that we can put in there later, or maybe it represents a number that we don't know the answer to it yet, and we're going to do some mathematics to find out what it is. So I think you recall occasions when you go to school camp and you're fighting over who gets the top bunk for their sleeping area. Usually there's one kid who just chucks all their stuff onto that top bunk and say, hey, that's mine. And that's exactly what's happening here with the turtle. She is throwing her sleeping bag on top of the bunk bed, and that represents her spot. She's not there yet. She's not lying in the bed right now, but her stuff is there as a temporary placeholder. So in algebra, so if I've got this thing down here, you may have encountered these little empty boxes in primary school, but in high school, we actually give these things a letter. So for example, the letter A is going to represent that missing number. And if you know a bit of mathematics, you can find out what the answer, the A, is supposed to be. But we're going to move on. All right, these letters can represent something like a variable. Look, letters in algebra can be called a pronumeral. It can also be called a variable. I'm just going to call them letters because when I say the word, you know what I mean. But when they are a variable, like force, mass, volume, time, all these sorts of things that actually represent something, you can link them together to create a mathematical relationship. So here I've got a relationship between the mass of one turtle is basically equal to the mass of two cats. That's what I've written down here in the row below. I've got one turtle is the same weight as two cats. If I translate this into algebra form, let me just undo here. I can use, let's say, I'm going to use the letter T for turtle, and there's only one of them, so I'm just going to write the letter T, is the same thing as two cats, and I'm using the letter C for cat. All right, so that's where the language of using letters and how we link them together or relate them together using equations like this. Just making you aware that, we use letters all the time for some very important equations here. So we've got Isaac Newton, and this is one of his many famous equations here. This is the force equation. We have Einstein over here, and we got his, energy equation. Look, he did so many important equations, but I'm keeping the simple ones here. And because these two gentlemen are from physics, these letters actually translate to what they mean. So they actually represent something here. So I've got mass, I've got acceleration, I've got force. Here I've got energy, mass again, and C is a funny constant letter. It represents how fast the speed of light is, and so he's got a letter. Instead of writing the really, really, really long number, he just puts a letter there instead. We've got Pythagoras here, who's famous for his work with triangles, and I've forgotten his full name, but this is Ohm, and this is his law here, Ohm's law. We use this for electronics, calculating current, voltage. So if I lay them out here, we've got current, voltage, and we've got resistance. Don't ask me why it's the letter I for current, but it just is. So just letting you know that this is the language you use to link or show relationships between things. All right, how to read algebra. So before I even get to equations, it's not going to work if you have some incomplete knowledge about how to read them properly. So I'm going to zoom in here, and we're going to fill them in. Side by side means multiplication here. So I've got 2a side by side. That actually means 2 times the a. Likewise over here, I've got the number 3 is right next to this bracket sign. So it actually says 3 times this bracket portion. Notice that I have written the letter X in a different way from the times symbol. And this is one of the reasons why we do this contraction in algebra is because we don't want people to be confused between the letter X and the multiplication symbol, particularly because the X is a very commonly chosen letter using equations. So we're not allowed to use them, but I'm just trying to help you understand when there is multiplication happening if you just by looking at it. Keep reading on. So numbers or letters with blanks in front of them are positive. So here's a number with nothing in front of it. That actually means a positive 8, and we've got the negative 4b. This one also has nothing in front of it, so that's actually a positive h, and you've got the other component, which is plus 6. That one's very, very important, and the reason why there's blanks, it's usually, if I write any number, so if I write the number 5, you automatically understand that means positive 5. I haven't needed to tell you that, you just assumed it, and that's the way we keep it as standard form. It's only when it's not a positive number do I actually apply a symbol to tell you that it's something different. If, yeah, just letting you know that. All right, another one here. Fractions means division. Again, we're not using the division symbol with algebraic form, so we hide them into fractions. In fact, a division sign is basically a fraction symbol here, okay? So this actually means m divided by 3. This will be very common. The sooner you learn that fractions are divisions, the quicker the whole solving process is going to be for you when we get to equations. Next one, plus or minus signs in front of numbers belong to those numbers. So let me put it to you this way. So looking at these different examples here, 5 take away f, that means 5, remember it's a positive sign from that earlier material, and this actually belongs to the f, so it's actually negative f. Going down, I'll switch colors here. I've got g, and there's nothing in front of it, so that's actually a positive g, and this plus sign belongs to the 3, so that's actually a positive 3. Down here, nothing in front of this 3a, so it's a positive 3a. And this negative sign is actually attached to the 4. So it's actually negative 4b. If you pick up on this, this would be so much faster when it comes to gathering like terms or simplifying things in the algebraic equations. All right, moving on. So now I think there's one more. Terms. Okay, I'm going to be using this word a lot, particularly when we get to the larger algebraic equations. So just keep in mind, terms are chunks of an equation or an expression. Look, an expression is just this sort of thing without an equal sign anywhere. But if you see an equal sign and it has left and right hand sides, then that's an equation. So these are going to be the main chunks. I'm going to highlight them in for you. So let me switch to a really big highlighter. So the chunks are separated by whenever you see a plus or minus sign between these segments. So here, I've got a chunk here, and I'm going to highlight the positive sign in front of it because that's the rule we had from earlier. There's another chunk over here. Now, I've made this one extra complicated because I want you to understand this as well, that if I have 2 chunks over a fraction sign, this is actually one mega chunk. So this is actually one giant chunk here. That's one term. Likewise, over here, I've got 2 little chunks, but they are wrapped inside the bracket and there's a multiplier in front of it, so this entire thing is one mega chunk. So how many terms are there in total? There's 1, 2, 3, 4 in this entire thing, and you could probably make an argument that these 2 smaller pieces could also be referred to as inside terms made. I don't think there's an official word for that, but I'm going to sort of move on from there, and that's a technicality that never really shows up or of importance for me. Like terms, again, there's a whole video, it's like half an hour long, where I go through every possible scenario and why some of the terms match. So if this explanation doesn't make sense to you, please go find that video. It was probably published maybe a month or 2 ago on the channel. It's pretty recent, so you don't have to scroll very far backwards into the timeline to find it. But like terms are terms that have matching letter combinations. It's a combination and they have to matching letters. So if I look for these letters, I've got the letter A, and I'm going to highlight all the ones that have an A in it. I can see the letter M, so let's just highlight all these M's in here. I can see another letter, which is the letter P. So there's the letter P. Okay, now we just go looking for which terms, which are the chunky bits, which terms actually match. Well, this term and this term, remember this is a positive, and this one here is a negative. These 2 terms match because they have the same letter combination. So I can actually stitch that together, and there's a process for that where you basically sum together the coefficients, which is positive 2 and negative 5 gives me an answer of negative 3 remaining. So the answer would be negative 3a. If that makes no sense, please go see the gathering like terms video. Other combinations out here that match, I can see that this term and this term actually match. The order of these letters doesn't matter. It's the combination that matters. Do they both have an M? Yes. Do they both have a letter P? Yes. Do they have one of each? Yes. Therefore, these two ones actually match. Looking over here, this term here, the 8M, it has no matching term that goes with it. It only has the letter M. Sure, this term and this term also has an M in it, but it's a different combination, so they don't actually belong. So this one can't be gathered with anyone else. Looking over here, this term here has a letter M. It also has a letter P, but why haven't I gathered it with these? The reason being is it's not the exact same combination. Do they all have the letter M? They do. Do they all have the letter P? Yes, they do. But the red term over here actually has two of them. Because when I translate this one, so this actually says negative 6 times M times P times P. That's actually two copies of the letter P. And now when I do that, can you see how this doesn't actually match those because they only have one P each. So they don't belong with the green terms I made earlier. So it doesn't have anyone to belong with. Again, there's a video, gathering like terms. I use cartoons and pictures and colorful uniforms to give you more ideas as to how to figure this out. But as long as you know what a term is and you can eyeball which ones match, that's going to make the whole algebra solving easier. All right, let's go to some rules with equations. Equations stay equivalent if you add or subtract the same amount on both sides of the equal sign. So I've got a giant icon over here. Actually, I'll just use the lasso tool. I've got an icon over here for the positives, addition, and an icon over here for subtraction. So for this rule, if you are going to add or subtract, you must apply the same amount to both sides so that it stays equal. And by equal, I mean that we got this seesaw over here. So we can say these two, everything on this side and everything on this side are about the same weight. Let's forget about the physics of how far away they are from the fulcrum. That's going to make this whole thing harder. But if we can just imagine that they could sit perfectly in the same locations on both sides, then what are we going to have? So I haven't actually finished this one here. So if I'm going to add a cat to the equation, I must add one cat to this side, and I must add one cat to the other side. And only then does it stay equal. Because if I didn't add a cat to my right-hand side, can you see it's now actually a little bit heavier on the left-hand side? It's no longer going to be equal. So I must add or subtract the same amount to both sides to maintain equal. Moving on. Now I'm just going to show you this without cats and turtles, of course. So here I would like to subtract 6 from both sides. So because I'm doing it to both sides, it should stay equal. My new result here, so 18 take away 6 gives me 12 left over. I've got this bit here. Now, because I'm going to subtract 6, I can actually just focus on this number here, this term, because it has no letters attached to it. So it's actually 6. This is actually a positive 6, by the way. Positive 6 and negative 6 cancels out to 0. Now, because it's now 0, I can just ignore that it exists there. It doesn't exist anymore. Now just copy down what's remaining there. So all that's left behind is this positive 2x. So I can write 2x because that little blank space in front of it implies that there's a positive icon there. So that's how this process works. When you multiply or divide, so again, I've got the icons over here, you must apply this globally to all terms on the left and right-hand sides. This usually doesn't become a problem if you are following the right sequence of events when you're solving an equation. However, when you get to the really complicated stuff that you see later on in high school, you may have to apply this. And usually this is where students come undone because they are used to adding and subtracting a small chunk to either side. And so they're thinking the same way where they multiply only some of the left-hand side and only some of the left-hand side. And you've actually broken the equal sign because it's no longer equal anymore. So when you do this process, if you have to do it, you must apply it to every term on both sides of the equation. So I'm using these characters or animals as a term. So there's only one term over here, which is a turtle. I need to double it. So here I'm going to put 2 turtles now. And on my left and right hand side, I've actually got 2 different cats. And so I'm treating them as different terms. So this one here, I need twice as many of those terms. So let me put another cat over here. So that's a chemistry cat. And I need another physics cat. And now it stays equal. Hopefully visually you can understand how this stays true. If I translate this to an actual algebra problem, here I've got an equation, and let's say I wanted to multiply. This wouldn't be the best way to start, but if I wanted to, this is what I'll have to do. I can see there's 2 terms on my left-hand side. They must each be multiplied by 2 for this to be to work out okay. Let's just do this one because it'll be the fastest. So positive 3 times 2 is going to give me positive 6. I can do the same thing here for the right-hand side. 12 multiplied by 2 should give me 24. Now I'm going to do this last term over here, that fraction chunky bit. This is actually going to cancel. So this actually says 5a divided by 2. If I then multiply it by 2, these two things actually cancel each other into a 1. So 5a divided by 1 turns into just 5a. So it's like I'm eliminating the bottom of the fraction by doing this. So that's actually going to turn into 5a. Yeah, that can kind of get a bit confusing. When you've got fractions and you want to get rid of the denominator, the bottom bit, if I want to get rid of this little number down here so that I can make the top portion free to continue working on for later, I must multiply it against the same number. So divide by 2 and then times by 2 is like undoing yourself. Like turn 180 degrees and then turn 180 degrees once more. It's like you're back where you started. So if I say turn to your left and then I say turn to your right, you've basically, sort of cancelling yourself there. All right, look, there's more work to be done here, but I'm just going to move on with the lesson here. To solve an equation, your goal is to isolate the letter on one side of the equal sign. So I would ideally want to have a equals the number. That's when I can get it to that point, I've finished the question. You can achieve this by using inverse operations, which is the opposite of these icons here, to cancel out the unwanted pieces, or now that I can use the word, terms. I can cancel out unwanted pieces or terms of the equation here. So here, I want to get rid of this 6 here. So and because I know how to read, this actually says positive 6. And this one, I may as well just put it over here. That means positive 18. So now that I've laid all the groundwork there, and I might even sort of color in my terms so you can see all the pieces we've got to work with. So they've been colored in. So what I want to get rid of that 6. So what's the opposite of positive 6? Well, it is to subtract 6. Now you recall this was an example in a couple of slides ago. So I'm just reusing it, and we're actually going to reach to the end point now. These two pieces effectively cancel to 0. And, 0 plus anything, well, there's no point of writing the 0 here because it's not really adding information at all. So now all that remains is just the green term, which is a positive 2x. So that term is still around. Look, I'm going to stop coloring in. It'll slow me down here if I keep doing that. Positive 18, take away 6. That should give me positive 12 remaining. And again, that positive icon is invisible because there's nothing here in front to block it. It's the beginning of, I'll just move on. Now the other piece I want to remove is this 2. So, and again, because I can read algebra, this actually says 2 multiplied by x. So the opposite of multiplication is to divide by 2. And I must apply this to both sides so that my equation stays equal. So if I'm dividing this with 2, then that just leaves me with 1x. Now, the number 1 as a multiplier is actually invisible. This actually should say 1x, but in algebra, we don't write the number 1 if it's a multiplication number 1. There's no point. The right-hand side divided with 2, so 12 divided by 2 is 6, and we are finished. Why? Because I've singled out the letter all by itself on one side of the equation, and there's a number of some sort on the other side. Look, the right-hand side could be like a decimal, it could be a fraction, that'll be fine as well. All right, moving on. Just as it is important to follow BOMDAS or BIDMAS or PEMDAS, whichever you've been taught in the past, when you're following those rules when you simplify, you must use the reverse order of operations when you are solving an equation. This is especially important if the equation has lots of those different icons in there. So this one here, look, we're just trying to see if we can find them all. So I can see there's actually a subtraction in this problem. I can actually see there's multiplication up here in the top because that's 2 times the letter A. I can see there's actually a division here because that's a fraction sign as well. So there's a mixture of operations in there, and therefore, because there has a mixture, I must follow reverse BOMDAS or reverse PEMDAS, whichever you have learned to use in the past. Use that as my guide to decide what do I target first when I'm using the inverse operations to isolate the letter. So let's do some examples. I've got 2. So I will do, and again, so I'll use that exact same scenario here. And above the page, what I've done here is I've actually written BOMDAS backwards, or PEMDAS. So BOMDAS. And so I must start with addition or subtracted terms first. Well, there's one over here in my left-hand scenario. That's my first target. Now it says -1 or subtract 1. So the opposite, my inverse for this first step is going to add 1 to cancel it out. So there's my +1. My second row of working here is going to be, well, my left-hand side with an extra 1 on it would be 21. This +1 basically cancels that to 0. So again, there's no point of writing 0 into my problem anymore. So I'm just going to pretend it doesn't exist anymore. And this bit is unchanged. So that gets copied down. 2a over 3. Now I follow, so since I've finished this bit here, I now run the protocol one more time. So I'm going to run this sequence again. What's my target? Do I have any subtraction or addition terms here? I don't. So I move to the next rank, which is division or multiplication. These are the same rank of importance. So it could be multiplication first or division first. Doesn't really matter. I do actually have a division this time round. Actually, I've got 2 choices here. I do have multiplication. I do have division here. I would go with the division because then I can eliminate the presence of a fraction very quickly. And I like to remove fractions where I can or cancel them out. So you may recall from the previous example, if there's a denominator down here and I want to remove it, I am actually going to multiply it against itself. So it'll be 2a divided by 3, then times by 3 again will basically cancel these 2 numbers out. So I must apply this feature to both sides. My left-hand side, once the 3 has been cancelled, just leaves me with 2a over 1. Anything over 1 is just itself. So 2 apples divided by 1 is just 2 apples. 5 divided by 1 is just 5. So I'm not going to bother writing the 1 underneath of it. That can just go away now. It's not needed. Now I'm going to struggle for a bit trying to multiply 21 by 3. So there was 63, I think. We're getting close. Now I run the protocol one more time. So I go back to the start. Do I have any subtraction or addition terms? No, I don't. Do I have any division terms? No, I don't. Do I have any I do have multiplication, which is over here. That says 2 times a. And to cancel that, I need to divide with 2. So I want to divide both sides of my equation with 2. And so that leaves me with just 1a or 1 apple left. And my right-hand side, because it doesn't divide cleanly with 2, I'm actually just going to leave it as a fraction. So this is perfectly acceptable to leave your answer as a fraction like that, especially if it doesn't divide cleanly. Look, if you have a calculator on a calculator exam, then why not? Just punch it into the calculator and see what you get. If you get an answer that has recurring decimals forever, then you probably should leave it as a fraction because it it means you don't have to round your answer. And rounding your answer just removes a little bit of preciseness from your answer. All right, my second scenario here, I'll run the reverse BOMDAS sequence again. So do I have any additional subtraction terms here? Yes, I do. I actually have this 10. Let me undo, there we go. This actually says plus 10. I want to remove that piece because remember this plus sign belongs to the fraction there. So I want to remove the positive 10. So the opposite here would be to subtract 10 from both sides. That leaves me with just the fraction component all by itself on the left-hand side of the equals, because positive 10, negative 10 becomes a 0. And there's no point of having, plus 0 on any side of the equation here. So that can just disappear. 16, to take away 10, leaves me with 6. Now we're down to here. So again, I run the process again. Sad mob, I think some people call it. I'm just going to call it reverse BOMDAS. So any addition or subtraction? No. Do I have any division or multiplication? Yes, I have division and multiplication. I'm actually going to knock out the 5 here because I want to eliminate fractions as soon as I can. I just hate them. They make algebra and equations a lot uglier when you're trying to work them. So remember this one says 4k divided by 5, so the opposite would be to multiply by 5, so that will be my operation to cancel it. Look, I'm being a bit messy here because I want to go quick, because there's a lot of slides here to go. So that leaves me with just 4k over 1, and you know the over 1 bit is no longer needed because it just doesn't change the answer. 4k divided by 1 is just 4k. 6 times 5 gives me 30. Now I run the process again. Look, I'm not going to scroll to the top of the page for time reasons. You're starting to get the hang of it. Reverse BOMDAS. I don't have any addition or subtraction. I don't have any division left. I just have the multiplication to undo here because that's 4 times k. So the opposite here would be to divide by 4. This isolates my letter k. And if I apply that to both sides, look, I forgot to write that little arrow here. So divide by 4. Because 30 won't divide with 4 cleanly, I'm going to use it and leave it as a fraction, and that's perfectly acceptable. And there we are, we're done. So both of them, I've isolated the entire thing down to one letter on one side of the equation. Moving on. Look, this will be a long video. I am going quickly as I can, but not too quick where you don't understand what I'm doing. When you have equations with brackets, you may need to use distribution law to open them up before you proceed. So just to give you a recap of distributive law, I gave a little cartoon to my students here. So the bracket portion is like some soldiers in a fortress. There's currently 2 soldiers there, 2 terms. And when you are using artillery in front of it, so for example, this 2 here, it represents this turtle with a cannon. The artillery outside is going to keep on firing into the fortress until they've shot every soldier in the fortress here. So this number 2 would shoot against this term and then shoot again into this term. And they'll keep on going if there's more and more terms inside the brackets. But most of these easy, simple scenarios only have 2 items usually inside of brackets. So here I got a 5, and this 5 is going to shoot and attack this soldier and this soldier. So if we do them one piece at a time, so 5 times apple, 5 times 1 apple should give me 5 apples. Now if we shoot again, so 5 times this other bit, now this is, remember, the negative sign belongs to that number. So I got 5 times negative 4, that's going to give me, and change color, it's going to give me a negative answer, so I put that subtraction sign here. 5 times 4 is 20. Okay, and that's how you expand it out. I've got another example here where it's a little bit more complicated. So here, the cannon, the attacker, is a negative letter instead of a number. Look, it's still going to work out the exact same way. So we're going to shoot in. So this will be attacking the first soldier, which is this positive 2. But we got negative k times positive 2. Well, negative times positive, well, negative wins. I put that sign down first. Now I can look at what remains. K times 2 will be 2k. For my next attack, it's going to attack this term here. I've got negative times negative. That's going to give me a positive answer, so I drop that down. Now look at what remains. So k times 3k. Well, it's going to be 3 times k, because you know that side by side means multiplication. However, we really should be using power notation now that we are in high school. So I'm actually going to change that to k squared. To square it means you multiplied it against itself. So if it was 3 k's together, that would be k to the power of 3, for example. All right, so that's distribution law. Let's apply it in scenarios where we have brackets. Okay, so here's a very basic one. So I've got 2 times the x. I've got it appearing twice. So there's a blue example and a red example. I'm going to show you what it looks like when you expand out the brackets, but I also want to make you aware that there's another approach you can use. So 2 times x will give me 2x. And then I've got 2 times negative 2 gives me negative 4. And then the right-hand side stays the same. I want to remove the purple term here, so I'm going to add 4 to both sides. That's just going to leave me with 2x and nothing else on the left-hand side. If I'm adding 4 to the right-hand side, that increases it up to 22. If I want to remove the pink 2, then I need to divide with 2, so that leaves me with just x. And if I'm applying the same thing to the right-hand side, dividing that with 2, I should get 11. Look, I'm not doing these little arrows around the outside because I do want to move a little bit quicker. If you are learning, if this is your first year doing solving equations, particularly for my year 7 group, please keep using those arrows or the alternative that I've shown you in class. But if you're out there and you're like a year 8, 9, 10, 11 student, then you don't have to put them on. In fact, it's not standard practice to leave them there. Think of them like training wheels on a bicycle. You eventually remove them once you know what you're doing. I just want to show you the alternative here. So in the first example in blue, I've opened up the brackets first, and then I did my reverse bomb dash to isolate the letter. There's another approach I could have taken, and I'll change to black ink here, and that's just simply to remove this 2, because if I look at reverse bomb dash, bomb dash, and I go backwards, you can see that multiplication division, I could actually start with that. While we're here, with reverse bomb dash, I have seen in the past students would go here in the rule and they start attacking this piece here. You cannot do that as your first move because it's trapped inside the fortress, okay? So because there's a fortress, you can't get access to the contents. You can't get access to those central soldiers. You need to deal with the cannon first to open it up if you want to get access, okay? So that's a very common mistake that students make. That's not allowed. So I can't access this 2 just yet. So I need to work with this. And I could just divide both sides with 2 to eliminate this because this actually says 2 times the bracket. So the opposite would be to divide with 2. That just leaves me with the fortress and there's no one outside, so they can come outside. So here they are, just all released into the wild. My right-hand side divided with 2 should give me 9. Now I want to remove the negative 2, so I'm going to add 2 to both sides. So my right-hand side goes to 9, 10, 11, and x there is all by itself, and we're finished. Now if we zoom out, this is the exact same problem, left and right-hand side, but I find the one on the right-hand side is more convenient because it's a very, very basic scenario where I didn't have to open the bracket. But I'll show you an example where you absolutely do have to open up the bracket. And that's because if I wanted to get rid of this 3, sorry, that's actually a negative 3, by the way. If I were to use the exact same trick I just applied by dividing everything with a negative 3, that means I would have to divide, this with a negative 3, so over 3. I have to divide this chunky bit, divide by 3. And I'd also have to divide this chunky bit with 3. Now, can you see how this is going to get pretty ugly because this does not divide cleanly with 3? This one happens too, so that seems okay. So we're actually going to we're going to create fractions, which is often making our job harder. So that's not the best first move. So in this scenario, the best first move is to actually open the brackets, like I sort of hinted at earlier. So we're going to use the trick here. Remember, this is a negative 3. That's a very common mistake. Students will forget it's actually a negative 3 that's attacking into the fortress here. So let's solve that one out. So that negative 3 times positive 2, remember there's a plus sign here. That's going to give me a negative 6. Now it's going to do the next attack here. So I've got negative times negative. That's going to give me a positive answer. Drop that down. So 3 times 3a, that's going to give me 9a. Now everything else has been unchanged, so I'll just leave them alone. Now I go looking, okay, from here, I actually noticed that there are some like terms here. This term and this term both have the letter A, the exact same letter combination. So they actually belong together. So these two combined should give us, 4 apples. This is positive, right? So positive 4 apples and positive 9 apples should give me positive 13 apples. That makes sense. And that negative 6 has not changed, so I'm just going to drop that down there. And again, the 24 has been unchanged. So all I've done from here to here is I've actually just converted and simplified. Now that I've gotten it as simple and converted as I can in a convenient way, I've just made it into a much simpler looking equation to keep working from here. So I'm going to use reverse operations to remove items here. So reverse BOMDAS, do I have any additional subtracting terms to get rid of? Yes, I do, which is that green bit there. So the opposite is to add 6 to both sides. So that leaves me with the positive 13 apples all by itself now. And my right-hand side with an extra 6 on it should give me 30. Continuing on, I need to get rid of the 13. So I'm going to divide both sides with 13. That leaves me with 1 apple. Remember that 1 is invisible now. And 30 doesn't divide cleanly with 13, so I'm going to leave that as a fraction, and we're finished. So in that scenario, we absolutely did have to open the brackets first. If you are trying to figure out just by eyeballing the question, when can I get away with not opening it? Well, you'll notice it when you've just basically got one chunky thing here and one chunky thing here. This scenario, we actually had multiple chunkies. So here's another chunky which has the fraction in it, and I had another chunky over here. So because it had many more terms involved, it's not necessarily the best move to start attacking that 3 from off the bat. Moving on, hopefully this video is not too long. If you have letters on both sides of the equation, you just need to cancel one of those terms using inverse operations. So there is a positive 6h term over here, and we've got another positive 2h term over here. I'll put a plus sign here because that's invisible. So we got the letters. The letter appears on both sides, and the trick is use inverse operations to basically remove the term. So I've got some choices here. Either I could use, instead of positive 6h, I could use negative 6h. That would basically cancel this out to a 0, leaving me with just a 3. So that 3 would be all by itself on the equal sign. Or I've got another option. Instead of removing 6h, I could remove 2h's. So if I take away 2h's, then this component turns into a 0, and that leaves me with a 4 on my right-hand side. Which do I do? Both are going to be valid moves to start, but one of them is going to make less work for ourselves down the road. Basically, the trick is choose the term you're going to work on such that you don't create more negatives in the working. So if I subtracted 2h from both sides, well, this can easily turn into a positive 4h. And we got 4 left on the... Okay, so that's what I get to once I've removed 2h. If I did the other occasion, which is to subtract 6h's, well, this left-hand side would just become 3 plus 0, so it's just 3. 2h's take away 6. Ooh, I'm going to get negative numbers now. So that's going to give me negative 4h. I've actually introduced negatives. And to me, that often makes things a bit uglier and harder to work with, because I'll need to cancel this negative sign a bit later. So I don't think that's the best way to start. It'll still work. Okay, we can still get rid of this 4, then we can divide by negative 4. It'll still work, but it's probably not the best starting move we could have done. So let's rewind time. I think our best move is to remove the 2h. It's the smaller of the two terms that match. So I'm going to do that. So subtract 2h from both sides. My right-hand side is going to just have 4 left behind. My left-hand side is, well, 3 is not affected. And 6h reduced by 2h gives me 4h. Now let's get rid of this 3. Remember, that's a positive 3 here, so the opposite is to subtract 3 from both sides, leaving with just 4h equals... if I'm subtracting 3 from the other side as well, that leaves me with just 1. And I'm running out of room here. My next trick is to divide by 4 to both sides. That leaves me with just h equals a quarter. And we're done. Look, that is pretty messy. If you take your time to be neat, this wouldn't look half as ugly or half as scary, but hopefully you see the steps that I'm taking here. And I am progressively going faster and faster because you should be more and more familiar with what I'm trying to do here with solving the equations. This one here, I've got the apple term is appearing on both sides. Remember that negative sign belongs to the two apples. Okay, so I got remember this is a positive 5a and I've got a negative 2a on the other side. So should I subtract 5 apples from both sides? Am I going to, is that move going to make more negatives? Yes, it will. Negative 2 apples and take away more apples is going to give me more negatives. There'll be negative 7 apples left behind. So I don't think it's the best move. So what I could do instead, so I'm going to rewind, how about we work on the other term, which is the right-hand term here, the negative 2 apples. What's the opposite of negative 2 apples? Well, it's to add 2 apples. So if I do that, then I cancel out the negative, and I just think the problem becomes a lot cleaner. So positive 5 apples plus 2 more apples gives me 7 apples, and the 3 has been unchanged. The 7 is unchanged, and this green term here has just cancelled out to 0. So plus 0 is not required because it's just empty space. And now I think that is a lot cleaner because I don't have any more negative terms. Now we use the reverse bomb dash sequence as usual, so I need to remove the 3. So I will, and I'll try to be neat this time, I'm going to subtract 3 from both sides. That leaves me with just 7 apples left behind because that plus 3 has been cancelled. My 7 take away 3 should give me 4 left over. Divide both sides with 7, I should get 4 over 7 as my final result. And here's a little curly arrow. Divide by 7. Divide by 7. And we're done. Oh yes, this is the end. Right, if your equation has powers, you may need to use square roots or cube roots to remove them. So a square root is this, and a cubed root is this. So if this little space here is blank, it means there's a 2 there. And if it needs to be anything bigger than that, then you need to write that number here. So let me show some examples here. I got 2 that are a little bit different. So here, if I solve this one, so I need to remove this term here first. So that leaves me with 5a squared is 30. That's because I've subtracted 3 from both sides. My next move is to remove this 5 here, so I'm going to divide with 5. And that leaves me with just the apples squared. Divide by 5 is 6. Now to finish the problem, looks I don't have enough room here, so I might move this one down to the next page. Keep things clean. To get it just to one apple, or one copy of the apple, I need to do the square root to both sides. That means I need to do this operation to both sides of the equation. This is not division icon, by the way. This has a bit of like a little, I don't know, beak in the front, like a vulture. I don't know if you can imagine, here's a bird and here's his wing and there's his legs. There's his face. Feathers. Look, I don't think it looks like much a bird now that I think about it, but it has a beak and that makes it a square root sign. I need to apply that to both sides. And when I do, square root of a square number undoes the squaring operation. So now I'm going to do square root to both sides, this little icon. That leaves me with just one apple, and I got the square root of 6. Now, I haven't got that to a final number. If I had a calculator, I would punch it in and see what I get. So I don't think this will be very common unless you have something that you can do the square root of really simply, like square root of 16 would be 4. Square root of 36 would be 6, for example, easily done in your head. However, if it's going to be square root of 8, then you would need to use a calculator. My other example, which I've moved to the next page, let me just move that down over here. This one's slightly different. So instead of a square root, we are going to use a cubed root, and I will try to save us some time by making a simpler scenario. So this one here, I'm going to remove this term here. Reverse bomb dash says I have to, so I need to add 9 to both sides, the inverse operation. That leaves me with 99 on my right-hand side, and x to the power 3 is left behind on the left. I want to remove the power of 3, so to achieve that, I'm going to apply this to both sides to do a cubed root. Now, the reason why I've used a cube root is because power 3 needs to be cancelled out with a cubed root. Okay? If this number here was a 7, then I put a 7 here and a 7 here, for example. And that's how you would do it. And you would definitely use your calculator for anything like cube roots or even higher. It's just I would never be able to do it in my head. Maybe some of you smart high school students can, but I certainly can't. So this will be a operation that you would use a calculator for, and this will be cubed root of 99. And I would use a calculator to get the final answer, but I don't have one right now, and I think the video is long enough as it is. So you would just punch that into a calculator, cubed root of 99, and get a number and write it in. And we're finished. I think that's it. Yeah, that's the end of my video. I hope this video hasn't been too long, but I've more importantly hoped that I've filled in some of the prerequisite knowledge you need on how to do these. The only thing that I really didn't go into in much detail was gathering like terms. And again, I just keep encouraging you to go to that video that I spent half an hour making for you that goes to all the possible scenarios of gathering like terms and simplifying. Well, I will see you in another video.